Hi everyone, welcome to week 11. This week is a little different in that the material that you are seeing is sort of mid or in between book publishings. So this information that you're about to see, you're only going to get from the slides. This is unfortunate as a result of how quickly the climate change material, changes, and the fact that the book doesn't really keep up with these changes as quickly as they probably should. So as a result, and I will send this in an email at the beginning of the week. So hopefully you will read this at some point before you do any homework and or take the quiz. But basically, this week is meant to be based on both packages. So the first package for this week is the climate modeling one, and that one I will let you go through it on your own. It's already posted on Blackboard. There's a link to the Google Drive where I keep the information. And this one is an update to the scenarios from AR5, and these are now based on AR6. So again, bear with me, lots of change, and unfortunate, it just prompts lots of really quick reaction. So future warming scenarios, I picked an image here from a California wildfire. They've been sort of in the news quite a bit, not so much in 2021, but definitely in years prior and probably years into the future. So what are future warming scenarios? So if you think about the idea of overall warming, if you recall back to the beginning of the term, it's been about 1.09 degrees Celsius, but between 18 up to 2019, based on the average from 1850 to 1900 and beyond. So this is observed warming. You can sort of break that down by how much CO2 has contributed, methane, nitrous oxide. Most of them in the red, of course, contribute to warming. Some in the blue, like sulfur dioxide and carbon and other aerosols, contribute to cooling. So when you add up all these columns, you get this. That's the basis or the basic point of this entire slide that looks super fancy and complicated. In the end, if you add all the positives and subtract all the negatives, you get this gray bar on the left. Okay, so it's about forcing. These forcing agents, carbon dioxide, methane, nitrous oxide, volatile organic compounds, and carbon monoxide, and black carbon, and halogen or halogenated gases, and aviation contrails have contributed to this much warming, okay, with the subtractions as you see in the blue. So what about the future? Well, the sixth report basically has some projections, and they are now called socioeconomic or shared socioeconomic pathways, SSPs. And there are 5 scenarios. The lower the number, the less harmful the scenario. That's the bottom line. So the 5 are meant to simulate a broad range of climate possibilities. So for example, the first scenario, or the lower 1 and lower 2 scenarios, show you a climate system that warms up a bit, but then levels off. And a lot of that is based on lots and lots of action taking place now in the immediate time frame of 2020 to 2040, doing lots of things to mitigate and curb carbon usage and rapidly switch toward alternative fuel energies across the earth, quite frankly. So this is what the 6th assessment report came up with. So let's look at the first one. And the first one is called, and they're sort of, in my opinion, a bit awkwardly named. So I sort of focus on, it's basically 1 to 1.9, 1 to 2.6, 2 to 4.5, 3 to 7, 5 to 8.5. So the number after SSP is the approximate radiative forcing by 2100. So this would be up to 8.5 watts per square meter. If you recall from that lesson going back, we're up to 2.72 watts per meter right now. So you would argue, well, why would we even think about this when we're already at 2.7? So we're already here. And the idea is if you begin to mitigate quickly, then you begin to slow down and things sort of revert back to something better. These assume no specific climate initiatives by governments, and they form the basis or the initial input to climate models. Okay, the scenarios are sort of split into time outcomes. Near term, 2021 to 2040, midterm, 2041 to 2060, and long term, 2081 to 2100. Later in the term, when we get into talk about adaptation and mitigation, people tend to break off into camps. Some people think, well, we need to do something now. The future is great and we need to deal with the future, but we also need to deal with the here and now. And so you tend to have people who are more adaptation versus mitigation. Again, we'll get into that when we get into that particular lesson. But this is how the basic setup of the SSPs are broken down. So let's look at the first one. And scenario SSP 1 to 1.9 or 1 to 2.6 means that the peak radiative forcing is lower than now, frankly, or technically as of 2019. The forcing stabilizes and there is a rapid and sustained limiting of negative human or anthropogenic climate change consequences. In other words, if we go this route, the clearly desired outcome, things look okay towards the end of the mid and towards the end of the century. Obviously, this is a desired outcome in my opinion. Now I'm giving you my opinion. This is not a very likely outcome, unfortunately. Right now, Europe, and this is as of 2021, it could change in 2022 and 2023, but as of right now, Europe is dealing with a real energy crisis that if they have a really strong winter or a cold winter and cold spring into 2022, they don't have enough carbon energy to warm themselves. They've done away with a lot of those dirty fuels, but they don't have enough of the other fuels to make up the difference. Always ask the question, what if it isn't windy? What if it isn't sunny enough to generate solar energy or wind energy? It's a good question to ask. So this is, again, the better scenario, the more significant one. If you look at it from the perspective of graphics, so this is what the temperature increase would be, or what we would expect the worst possible scenario to be in 1.9 and 2.6. So the total observed for 1.9 or 2.6, obviously we approach 2 degrees, but we never go over it. And ideally, that's where we would want to remain as a global community. Again, is that likely to happen? In my opinion, I guess, and I want to be clear about that, probably not. Now, the next one, 2 to 4.5. So the radiative forcing stabilizes somewhere in the middle part of this century. There's still a continued increase in greenhouse gas emissions, and I find this to be probable simply because you have China and India and other developing countries that are not likely to, even though they are well-meaning and they want to go into clean energy and all that, chances are the increase in greenhouse gas emissions will continue. There is still the stuff that's been put into the atmosphere since. And so this is likely to be the more reasonable expectation. And again, a lot of this I'm giving you personal opinions, so take that with a grain of salt. Again, continued greenhouse gas emissions, more than likely because you have continuing economies that are growing. You're still going to have an incidence of extreme events that's likely to continue. They're happening now, so there's no reason to believe they wouldn't happen in a future where we reach this. Remember, we're at 2.7 right now. Now, robust greenhouse gas emissions are employed, and that's a good thing. But again, my opinion, this is a more reasonable expectation to have. And this is what it looks like from a graphic perspective. We go over 2 degrees total, and this is the change in temperature by 2081 to 2100. But we don't make it to 3. And so most people, most scientists would love for us to remain below 2, but chances are we're headed to a world where we're probably going to be above 2, but less than 3. So this is sort of the middle range scenario. Now, scenario SSP 3 to 7.0. This is where it gets a little scary. There's the implication that movement is slow, high emissions continue, and as a global community, we sort of let things go until we reach about 7 watts per square meter. 7 watts per square meter increase in radiative forcing. If this is the case, not only does it imply a rapidly warming Earth, but it also implies a continued decrease in air quality. So that has its own negative consequences besides warming. That has respiratory disease issues that you have to deal with. In this case, a reduction in greenhouse gases as a global community is far less effective. That's what that looks like. Above 3, approaching 4. And here, some of the negative consequences could be even stronger, severe weather events, catastrophic rain / drought, depending on where you are. And this has negative consequences basically into the 22nd century, which I realize sounds really far, but this is what we're talking about, the long-term part of the century, 2081 to 2100. Finally, the nightmare scenario. In this case, the greenhouse gases continue to increase. It continues unchecked. Radiative forcing stabilizes around 8.5, but by that point, what this implies is an Arctic Ocean to be ice-free under the scenario during the summer. Global sea level rise of 1+ meter. That's more than 3 feet. If that's the case, you have places like Bangladesh, London, parts of Miami, New Orleans, New York City. Many island nations like Vanuatu and Kiribati and the Maldives in the Indian Ocean and other such small places are already going to be severely impacted by this. Clearly the nightmare scenario. And that's what that looks like. Temperatures globally 4 degrees or higher at that point. So now, again, what about the future? Let's continue. So scenarios don't consider emission reduction strategies by government. They just simply tell you, if we let it get to this point, this is what would happen. In other words, if we do nothing, sort of a business as usual model. This is what the numbers look like for all those scenarios, looking at it on a tabular mode. So the near term, the midterm, and the long term. The estimate, you get an estimate, you get a likely range. So in estimate 1.9 or 2.6, we basically level off here with a range of 1.2 to 1.7. All these are manageable, quite frankly, in the near term. Now, go into the midterm and you get into the two uglier scenarios. We're talking about 2.1 to 2.4. That's basically double what we have now. And then in the long term, 3.6 to 4.4. And even the low end of those ranges are bad. So, and again, this all comes from the IPCC Summary for Policymakers. That's what that SPM stands for. This is, again, looking at those scenarios. This is looking at Arctic sea ice coverage in September, which is when it's usually at its lowest. Notice that the better the scenario, the more ice remains. So there we go. Even in the best scenario, ice coverage continues to decrease in all of them. But, let me go back. But in these last three scenarios, 4.5, 7.0, and 8.5, the Arctic Ocean becomes ice-free at some point, meaning it's just ocean. There's no ice left. Okay? In the bottom two scenarios, some ice remains. Now, this is global surface temperature, and this is where we are, or in the model here began in 2015, but as you move towards the future, the two lower scenarios, notice how they level off, and they even begin to go down a bit, but you level off below 2. Whereas 4.5, 7, and 8 clearly continue this trend we have been on. And again, this is AR6, Working Group 1, Summary for Policy Makers. Now, why is temperature rise so uncertain? There are 3 factors: climate sensitivity, lag of climate behind greenhouse gases, meaning it takes a little bit of time before you experience that increase in temperature, and the carbon cycle feedback. Factor 1, we're about 415 parts per million right now. So how much does temperature rise if we double CO2? So if we increase from 280, which is what it was back in 1750, to 560, what would that mean? The best estimate is that, which you already saw in those graphics, anywhere between 2 and 4.5, which means that we continue to increase carbon dioxide in the atmosphere at a rate of 2.5 parts per million per year. So every year you add 2.5, 2.5. So in 2 years, you've added 5. In 4 years, you've added 10, and so on and so on. Factor 2, how fast does climate change catch up with a change in greenhouse gas concentration? Remember, the oceans have absorbed over 90% of all the CO2. So at some point, the oceans cannot absorb. It's sort of like you can only put so much carbonation in soda water. And when you put too much, it bubbles out like a fizz, right? So oceans cannot absorb heat forever, and they cannot absorb carbon dioxide forever. So at some point, that heat is released back into the atmosphere. In factor 3, the carbon dioxide cycle, or the carbon cycle, basically. This is frankly more important for the mitigation, and when we get to that in a subsequent lesson towards the end of the course, mitigation is the things you do to fix the problem. And so how much CO2 will be taken out of the air by oceans and the forest? These are the two natural processes that can take carbon out of the air, right? Trees take in CO2, they convert it through photosynthesis into a sugar molecule and oxygen. And then oceans absorb it, and that carbon goes into seashells and all kind of stuff. So now, if forests are susceptible to droughts and pests and fires, you may turn these sinks, which is where you sort of store carbon away, and you may dump it back into the atmosphere. So at one point, we don't know exactly when these sinks turn into sources. And if they turn into sources, now you're dumping more of this into the air, making the problem worse. Think about the fact that Arctic global warming is double the global average. So the heating is more obvious and more stark at those latitudes. It's greater over the land than over the ocean. And the smallest has been over the North Atlantic. And this is possibly related to the slowing down of the ocean conveyor belt circulation. Remember the thermohaline back in the beginning of the term? That's what this is related to. There are other potential future scenarios, regional patterns, less snow cover, extreme hot events, heat waves, heavy rains. Some places may have too much water, some may have too little. Ocean acidification, which means coral and other tropical ecosystems may be affected. Stronger tropical cyclones, maybe not necessarily more of them, but definitely stronger if they do form. And tropical storms may move a bit further north as a planet warms. So these are some of the possible regional issues that may happen. Less snow cover. Obviously, this is not a problem in the Caribbean, but perhaps it could be a problem in the northern United States, in Europe, and in Canada. So lots of sort of rearranging of the norms. Here's a look at precipitation. And again, in the near term, 2021 to 2040, 2040 to 2060 midterm, and 2080 to 2100 long term. So here's the idea of, does it get drier or does it get wetter? And notice, the amount of water in the atmosphere is still the same. It's how that water is distributed. That's an issue. Given where people tend to live and where population centers are. So, in the brown, you see drier than normal. In the green, you see wetter than normal. And this low likelihood scenario, the dashed line you see here, is a potential true worst case scenario where sea level suddenly rises even more than models indicate. So we're talking about, instead of a meter, which is about 3 feet, now we're talking about 1.5 to close to 2 meters. Now you're talking about 4 to 6 feet. And that would have dire consequences in almost every coastal city you can think of. Miami, New York, Boston, Tokyo, Shanghai, Hong Kong, London. Think of cities near the coast, and chances are they would have a significant impact under this true worst case scenario. Or the idea of pH, meaning as ocean pH gets lower, the acidity of that water is lower, or it's more acid, so the acidity is higher actually. And as a result, this has a significant impact on marine life, corals, and any sea creatures that form shells from calcium carbonate. Calcium carbonate is very easily dissolved in acidic water. So therefore, you could destroy ecosystems like coral or any animal that has a shell. And so as a result, this could have a significant impact on the food chain, which would eventually impact us as well. So some of the other future scenarios, potentials, these are some of them here that you can see. Contraction of the Greenland ice sheet, slowing of the conveyor belt, tropical precipitation decreases, and increases in high latitude precipitation. So you're redistributing the amount of water that is found. Finally, under the worst case scenarios, so remember the better scenario, the worst scenario. In the worst scenario, more of that carbon goes into the atmosphere. More of it goes into the ocean. More of it goes into the land. Obviously, these higher scenarios imply more damaging effects. Okay, so at some point, the ocean can handle all that CO2. So if it can go into these sinks where they are stored, in these worst case scenarios, it goes into the atmosphere. And if it goes into the atmosphere, we observe it quite quickly in the form of more severe weather, droughts, extreme precipitation events, and so on. So again, this is a very quick turnaround for this type of lesson, simply because the books haven't caught up to where the IPCC is. So I highly recommend that you focus on the slides for the information for this lesson. Otherwise, if you have any questions, please come to the live office hour, or send me an email, or ask away. Otherwise, I hope you're doing well, and I will talk to you soon. Bye.